So, today we are going to be talking about applications of depth first search. In the last class we looked at the depth first search procedure. We will also be discussing the running time of depth first search today, and then looking at an application of depth first search to checking if a given graph is 2 edge connected. Yeah. Okay, so recall what we did in the last class. We wrote a small piece of code, depth first search V. Can someone tell me what this was? So, the first thing we do is we set visited V equals 1, let us say, and then okay, I will not worry about the counters for now, because that is for all W adjacent to V. He was saying children of V, there is no notion of children of a node in a graph. Yeah. So, for all W adjacent to V, if visited, if not of visited W, then DFS V W, that is it. Yeah, that is what we said our DFS procedure is. It first marks the node as visited, then it will start the DFS on each of the adjacent nodes, provided they have not already been visited. That is what DFS V corresponds to. Okay. How much time does this procedure take? It is a recursive procedure. So, you have to do something careful, some careful analysis of the running time. How much time does it take? Why? Pardon? Compared, what do you mean by compared?
We have to check the end is visited or not.
For every edge we will have to go, we will have to look at that edge twice. Okay. Yeah, the answer is right. You are basically doing a total time of order m. Actually, I can just say order m, because I am assuming that the graph is connected. Yeah, in a connected graph m is at least as large as n minus 1. So, you can always say order m. So, let us just say order m, and we have assumed graph is connected. Okay. Now, let us try and see what is happening here, right. And for this I am going to use my adjacency list representation, because that will also give you a better picture of what this is. So, recall that in the adjacency list representation of the graph, there will be one entry corresponding to node V. This would be the adjacency list of V, the nodes which are adjacent to V. Yeah. If a node X is adjacent to V, then V is also adjacent to X, because it is an undirected graph. So, X की list में भी कहीं पर V आएगा, कहाँ पर आएगा उससे कोई मतलब नहीं है, पर आएगा कहीं पर, right. When I do this step for all W adjacent to V, what does this say? How will I actually translate it into code? This is pseudo code, right. You do not really have a statement like for all W adjacent to V. What will you do? You will write, you will basically have to traverse this list, right. For that you will have one pointer which points to the first node, and then when you have visited, when you have looked at this node, then you will update the pointer to point to the next, and so on and all till the pointer becomes null, right, or the reference becomes null. Then you would have reached the end of the list. That is what you will, that is how you will actually be implementing it, right. So, basically every time I go through this loop, I advance that reference, I advance that pointer by 1. Yeah. Okay. Now, if this was the very first node U and it was not visited, then what would I do? I would start a DFS on U. Yeah. As a consequence, I will do some other computation, and when that computation finishes, I come back to this DFS procedure, the DFS that I was doing on V, and I retrieve that pointer. Essentially, I would have that the pointer is still pointing here, that because that was a local variable, so to say. Do you follow what I am saying? I would not start. So, suppose okay, let me say I advanced through this pointer, this was a longer list and I reached this pointer, reached at this point, let us say this node is A, okay, and A was not visited. So, I went and did DFS of A. When I came back from DFS of A, then what is the next node that I will see in this for loop? I will go beyond this, beyond A. I would not continue, I will not start all the way from the beginning. And how am I retrieving the fact that I was here last, this pointer was pointing to this information? This is coming from the recursion. The fact that in a recursion, when I make a recursive call, I store the local variables. ये समझ में आ रहा है फंडा? नहीं. देखिए, okay, if I were not to write for all W adjacent to V, I would have written something like the following. I would have, let us say, let us call this array A. I would have P equals A of V, right. What is P? P is this pointer of V. So, P initially is pointing to here, right, and I would be replacing this by while P not equal to null, good, something like this. This might not be completely correct, but it will be something like this. While P not equal to null, what would I do? I will do something like this and then I will do P equals P dot next. Yeah, you understand what this is. Basically, each one of them has a next rule, and this W will be P dot data or P dot node or some such thing, right. What is W? Because we do not have a notion of W, right. So, it will be P dot data, let us say, right. So, basically I am saying each one of these nodes has two members, one is data and one is next, right, and P is referring to this. Why am I going into all of this, right? So, if I have to replace this line, I would have to do something like this. This is how you will actually code it up. Yeah, and this while loop, this braces ends here. So, the while loop will now have these two statements in it. Why am I doing this? Because now when I make, so now note that visited is not a local variable, visited is some global array. The only local variable that I have here now is my P. When I make this recursive call, this P is stored on the stack, so that when I return from this recursive call, when I finished DFS of A, I was, so let us now say P was pointing to here, I am doing DFS of A. When I return from here, I will retrieve this P back, and I will increment P, or I would advance P like this. So, P would now point to the next one. I would come back to this P, I would not come back to this P, right at the beginning or some such thing. Why am I saying this? This is crucial for the running time of the procedure. You can understand why. Because if every time I was going to start from the beginning, then I can't say order M. I am now using the same fact. I will be traversing this list only once for each node, right. पहले मैं इस नोड पे इसको रेफर कर रहा हूँ, फिर इसको रेफर कर रहा हूँ, फिर इसको रेफर कर रहा हूँ. इसको रेफर करने में हो सकता है मुझे DFS U करना पड़े, और DFS U करने में मुझे और बहुत सारे नोड्स की एडजेसेंसी लिस्ट में ट्रैवर्स करनी पड़े. पर किसी भी नोड की एडजेसेंसी लिस्ट में दोबारा, मतलब once I start traversing the adjacency list of a node, I don't repeat any entry in it. I kind of just keep moving forward in that adjacency list. Yeah. So, what does that mean? For each node, I am effectively spending time proportional to the degree of that node. Sum of the degrees of the nodes is the number of edges, 2 times the number of edges in the graph, and so the total time required is order M. Yes? She said each edge is visited twice, that is also true. V x x v, the edge V x is being looked at here when I look at this node, because x is now treated as a adjacent node of V, and the same edge x V x is looked at here when I look at this node x, because V is being treated as an adjacent node of V, right. So, actually every edge is looked twice, exactly twice, yeah, and this gives you the running time. Is this clear? We are heavily using the fact that this is a recursive program, and when this recursive call finishes, we retrieve this particular local variable. This local variable gets back the same value it had before this recursive call was made, right. So, now if I told you that implement DFS without using recursion, you will have to use a stack. You will essentially simulate the recursion by using a stack, but now it should be clear what variables will you store on the stack. What information would you store on your stack? Basically p, the value of p. So, in the case of recursion, two things are stored actually, not just p. Someone else has to tell me what else is stored. V, local variables, जो भी procedure था, that procedure के जो local variables थे, they are stored, and the parameters to the procedure are also stored. So, the parameters to this procedure is V, that will also have to be stored on the stack. Of course, the stack also stores return address and stuff like that, but those things you do not need here, because you know exactly where it is returning to. Yeah. So, this will be your 6th assignment. Okay. You will have to implement it, I will give out the details later, but you will have to implement DFS without using recursion, so that you understand this well. Great. So, we have looked at DFS, we have classified the edges as tree edges and back edges, okay. And we have looked at what the running time of DFS is. One other thing that perhaps we should do before we proceed further is look at this distinction between tree edges and back edges once more, right. So, tree edges and back edges, right. Suppose I have an edge uv which is a tree edge, and if uv were a back edge, let us see what can we say about the relation between the arrival times and the departure times for the nodes u and v. Okay. Let us see, let me ask you these questions. Suppose I tell you that the arrival time of u was less than the arrival time of v. Yeah. That is, I reached node u before I reached node v. Pardon? UV form a back edge. Right. Suppose I told you that I gave you this information. I reached u before I reached v. Now, what is the relation between the departure times of u and v? Departure of v is greater than or less than? Departure of u is less than or departure of v is less than? देखिए, you reached u first, uv is a back edge, you reached u first and then you reached v. So, what does that mean? V is a descendant of u in the tree. Yeah. देखिए, uv is a back edge, so there has to be an ancestor descendant relationship between the nodes of uv. One has to be an ancestor of the other. Which is an ancestor of which? Clearly, you will reach an ancestor before you reach the descendant, because you are coming down from the top of the tree. So, u is an ancestor of v. In fact, I have shown that in the picture essentially, right. So, u is an ancestor of v. If u is an ancestor of v in this tree, then first I would have finished v and only then would have backtracked all the way and come back to u and finished u. No, this is for the back edge. Right. Okay. So, this is not a tree path, sorry. So, there is some tree path between u and v also, of course, and let us say this is the edge uv. There are other nodes on this tree path. So, you would have finished a descendant before you move up, right, because that is how you backtrack. You finished a node and then only then you move back up, and then you finish that and you move back and so on. So, the departure time of u is more than the departure time of v. We would have left v, we would have finished v before we finished u. Okay. What if uv is a tree edge? Would that make a difference? Suppose once again that arrival of u is before arrival of v. If arrival of u is before arrival of v, then u is a parent of v. So, u v, u v have a parent child relationship, not just an ancestor descendant, but a parent child. U is a parent of v, right, because it is a tree edge, u v is a tree edge, right. So, when I depart from v, after that only will I depart from u. So, departure time of v is less than the departure time of u. Note, I cannot say that the departure time of u is one more than the departure time of v, because it might have more children. Similarly, I cannot say that the arrival time of v is one more than the arrival time of u, because there could be other children also. Yeah. So, the relationship is the same, but right, these are the same relationships, but they are coming from different reasons. Roughly the same reason. Okay, agreed, granted. Okay, now let us look at an application of depth first search to determining if a graph is two edge connected. So, let me write down. Connected, right. So, that is the term that I am going to be using. G, a graph G is two edge connected if and only if G minus E is connected for all E क्या हो गया ये? I am saying take any edge, capital E is the set of edges. When I write graph as V comma E, V is the set of vertices and capital E is the set of edges. Little e is an edge, G minus E matlab remove the edge from the graph. If it is still connected, and this is true for every edge of the graph, then we say that the graph is two edge connected. Right. So, in words, a graph is two edge connected if it remains connected even after the removal of any edge. Yes, only one edge. A graph, so a graph is two edge connected if and only if it remains connected after the removal of any one edge. Okay. So, let us see. Is this graph two edge connected? If I remove this edge, then it becomes disconnected. Such an edge whose removal disconnects the graph is also called a bridge. This edge we would call it a bridge. Okay. So, this graph is not two edge connected. Is this graph two edge connected? Yes. So, a graph which is two edge connected will not have any bridge edge. A graph which is not 2 edge connected will have a bridge edge. Okay. Why do you think this notion of 2 edge connectivity would be useful? Right. So, if this were a computer network and some link fails, right. So, then you are interested in whether the network is still connected or not. Right. So, if your network was 2 edge connected to begin with, then no matter which links fails, your network can still keep functioning because it will still remain connected. But if the network were not 2 edge connected to begin with, then the failure of a link can cause the network to break down into disconnected components, so that messages cannot go from one side of one connected component to the other anymore. Yeah. So, this is basically measuring reliability of the network. So, now the question is the following: I give you a graph and I ask you, is it 2 edge connected? How will you check if it is 2 edge connected? Right? Anyone?
So you can use DFS and check if we can reach from the other. Suppose we have reached from one endpoint to the other endpoint of an edge, and then from if we can reach the other endpoint.
For each vertex, if we can find a cycle, then it will be.
For each vertex, if we can find a cycle. How? How will you check if a given graph is 2 edge connected? And you have to do it fast. Fine?
We look at the departure time.
If you look at departure times.
So between any two nodes, there should be a tree edge also and a back edge also.
Between any two nodes, there should be a tree edge and a back edge.
Not necessarily.
हर एक नोड के बीच में ट्री एज भी हो, बैक एज भी हो,
Either he is trying to say that between any two edges you have two paths. So on removal of either of one, it still remain connected. Either he is trying to say that.
चलिए DFS नहीं यूज करते, बिना DFS यूज करे आप कर सकते हैं कोई तरीके से? हाँ? Each node should be visited twice.
Between any two nodes.
Okay, don't worry too much about DFS because it's not straightforward, but you will see how to do it. Yeah. Let's see. Can you check this property of 2 edge connectivity by some other mechanism? Yeah, BFS. Yes. What will you do with BFS? So you have to check if the graph remains connected even after the removal of an edge, right? So take an edge, remove it, check if it is connected. Then take another edge, remove it, check if it is connected. Take another edge, remove it, check if it is connected. तो कितना टाइम लगेगा इसमें? ऑर्डर mn लगेगा, m स्क्वायर लगेगा, m स्क्वायर लगेगा. m एजेस हैं और हर एक एज के लिए आपको एक बार BFS रन करना पड़ेगा. BFS में टाइम ऑर्डर m लगता है अगर कनेक्टेड हो तो. ठीक है, तो ऑर्डर m स्क्वायर लगेगा. तो दैट्स मोर एक्सपेंसिव, राइट? सो वी कैन do it in order m square by removing every edge and checking if resulting graph is connected. Yeah. Yes, but that's expensive for us. So we want to do something in order m time, linear time. If every vertex has a back edge, then only then is the graph 2 edge connected. देखिए एक बहुत सिंपल सा एग्जांपल है. आप कोई भी एक साइकिल अगर ले लें, ठीक है, इज द साइकिल अ 2 edge connected ग्राफ? इट इज़ 2 एज कनेक्टेड राइट. कोई भी आप एज निकालेंगे तो ये कनेक्टेड रहेगा. साइकिल पे अगर मैं ब्रेथ फर्स्ट सर्च करता डेप्थ फर्स्ट सर्च करता हूँ तो क्या बनेगा मेरा? व्हाट विल बी द ट्री एजेस? मैं यहाँ से मान लीजिए यहाँ आया तो फिर यहाँ जाना पड़ेगा, यहाँ 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 यहाँ, और अब यहाँ से मैं बैक ट्रैक करना शुरू होऊंगा राइट. सो दिस विल बी माई DFS ट्री, द वन इन रेड, एंड द ओनली बैक एज विल बी this last edge. So my DFS tree, if I were to draw it differently, would look like this. It would be a path, my DFS tree, with one back edge only. Okay. ये तो 2 edge connected है, तो from every vertex between any 2 vertices वो सब गलत हो गया. एक बैक एज है इसमें जोड़ घटा के, पर ये 2 एज कनेक्टेड है.
Analogously, like whenever you are backtracking
हाँ
from that vertex, if you get a back edge, that means there is a cycle connecting that particular path of traversal. So you can then conclude something.
good, we are getting somewhere. So let's develop this one step at a time. So I did a depth first search. So clearly we have to do a depth first search, right? Suppose this is the depth first search tree I obtained, right? I have just drawn the tree edges. There are other back edges, I have not drawn them yet. Now when I am backtracking out of this node, backtracking means I am going back up, right, because I have explored this entire thing. What do I require? I have explored this entire thing, I have not yet gone here. So, I have come from here, I came like this, I came like this, I explored this entire thing, now I am backtracking, right. I want to ensure that this edge along which I am backtracking is not a bridge. I want to ensure that it is not a bridge. Okay? What will ensure that this edge, I am only interested in this one edge not being a bridge. What will ensure that this one edge is not a bridge?
There is also backage from
There is a back edge from where?
from this vertex.
From this vertex?
From your backtrack.
From this vertex? इस vertex से होनी चाहिए back edge? देखिए ये एज अगर इस पूरे, इसलिए मैंने इसको रेड से सर्कल भी कर रखा है आपको, एनी ऑफ दीज वर्टिसेस से अगर कोई बैक एज यहां नहीं, मतलब इसके किसी भी पेरेंट पर जा रही है, और भी आगे हो सकता है, डोंट इमेजिन कि ये रूट तक जा रही है, मैं ये नहीं कह रहा हूं. अगर यहां से कोई भी बैकेज किसके, इस नोड के किसी भी पेरेंट पर जा रही है, या यहां जा रही है, या यहां जा रही है, या यहां जा रही है, यहां जा रही है, तो ये वाली एज ब्रिज नहीं हो सकती. क्यों नहीं हो सकती ब्रिज? इसको हटा दीजिए इस एज को, तो डिस्कनेक्ट हो गया ग्राफ? नहीं. क्यों नहीं हुआ? यहां तो एक ट्री है आपके पास, ये बाकी भी ट्री है, तो ये दोनों कनेक्टेड हो गए, और इन दोनों ट्रीज के बीच में एक एज है, तो पूरा का पूरा कनेक्टेड हो गया. देखिए अगर आपने ये एज, इफ यू रिमूव दिस एज, राइट, लेट्स लुक एट द ब्लू ट्री, the DFS tree. In a tree, when I remove one edge, I will get 2 pieces, not more. Yeah, this will be one piece and the other remaining piece. I cannot create more than 2 pieces by removing an edge. I create exactly 2 in a tree. Now these 2 pieces are connected amongst themselves by the tree edges, by the blue edges, right. So I can go from any node to any other node. How will I go from a node in this piece to the other piece? By going from that node to the end point of this green edge, taking this green edge, going there, and then going from here to whichever node I wanted to go to. So, which means that every pair of nodes is connected, which means that the entire thing is connected even after I have removed this red edge. So, this red edge is not a bridge. So, if such an edge is present, then this edge is not a bridge. इसके लिए रिक्वायरमेंट ये नहीं है कि यहां से शुरू हो, इसमें से कहीं से भी शुरू हो. और कहां जा रही है ये? देखिए, ये किसी एंसेस्टर पे ही जाएगी, इसके किसी एंसेस्टर पे ही जाएगी. अगर ये एज यहां जा रही होती तो भी हमारा काम हो जाता. अगर ये एज ग्रीन वाली यहां से जाने की जगह यहां तक ही जा रही होती, तब भी ये एज ब्रिज नहीं होती. ठीक है, बट इट हैज टू गो टू दिस नोड और बियॉन्ड. अगर ऐसी कोई एज नहीं है तो तब क्या ये एज ब्रिज है? यस, क्योंकि जब मैं इस एज को रिमूव करूंगा, आई विल गेट टू पीसेस विच आर डिस्कनेक्टेड फ्रॉम ईच अदर, बिकॉज नाउ देयर विल बी नो एज गोइंग फ्रॉम हियर टू एनीवन हियर, because we said there is no edge of this kind, right? ये वाला जो पीस है जो मैंने ये रेड में बना रखा है, और जो दूसरा पीस है ये जो बाकी का है, इनके बीच में कोई कनेक्शन नहीं बचा. ऐसा क्यों नहीं हो सकता कि कोई एज यहां से यहां जा रही हो ऐसे? वो तो जाएगी एंसेस्टर पे ही जाएगी, तो ऐसी एज तो हो ही नहीं सकती है, वो तो एंसेस्टर पे ही जाएगी. और अगर एंसेस्टर पे जा रही होती तो हमने उसको कंसिडर किया होता. अगर हमने अभी कहा कि एंसेस्टर पे कोई एज जा ही नहीं रही है, तो इसका मतलब कोई कनेक्शन ही नहीं बचा. ठीक है, सो दिस इज द कंडीशन वी हैव टू चेक. Everyone understands? So, what is the condition we have to check? When I backtrack from a node, I have to check that there is some edge from here which is going to an ancestor of this node. ठीक है? How will I check this? लीनियर टाइम में करना है सारा काम. समझ आ रहा है मैं क्या कह रहा हूँ? और ये काम हर एक एज के लिए, हर एक नोड से जब हम बैक ट्रैक कर रहे हैं तो हमें ये चीज़ चेक करनी है कि नीचे से, उसके नीचे से कोई एज आ रही है. नीचे से समझ रहे हैं आप? मतलब उसके जो डिसेंडेंट्स हैं उनसे कोई एक एज जा रही हो उसके एंसेस्टर पर. There should be some edge from its descendant to one of its ancestors. That's all. So let me write it down in words. So when backtracking from a node V, we need to ensure that there is a back edge from some descendant of V to some ancestor of V. किसी डिसेंडेंट ऑफ V से किसी एंसेस्टर ऑफ V पर एक एज जानी चाहिए. अच्छा, एक चीज यहां ध्यान रखिए, हमने डिसेंडेंट ऑफ V में V खुद भी इंक्लूडेड है. अगर ये एज ना हो पर यहां से ही एक एज जा रही हो तब भी हमारा काम हो गया, क्योंकि तब भी ये ब्रिज एज नहीं है. ठीक है, सो आई हैव सेड डिसेंडेंट without saying proper descendant. So descendant includes the node itself, but this ancestor is a proper ancestor, which means parent or above. ठीक है, now we have to somehow ensure this. How will we check this property? And we have to do it all fast, क्योंकि we are only permitted order m time. हाँ.
Keep track of all the packages, and when we backtrack from particular node,
हाँ.
we delete from our record that particular package which ends on that node.
But that is order deleting a particular.
Keep track of all packages. Do we need to keep track of all back edges?
So, sir, we delete which are inside that particular.
राइट देखिए हमें क्या मतलब है इस नोड से इसके डिसेंडेंट से आई एम इंटरेस्टेड इन अ बैक एज राइट बट डू आई नीड टू कीप ट्रैक ऑफ ऑल द बैक एजेस स्टार्टिंग फ्रॉम which is the back edge which is of interest to me देखो if we keep track of every back edge then we are going to be spending a lot of time right but there is one back edge which is of interest to us which is the one back edge which is of interest to us जो सबसे ऊपर जा रही हो क्लियरली इफ आई नो कौन सी सबसे ऊपर जा रही है तो वो इसका भी काम करेगी और जो और बीच बीच में आ रहे हैं उन सबका भी काम कर देगी वो सबसे ऊपर बैकेज को इंग्लिश में कहते हैं डीपेस्ट बैकेज ठीक है यू अंडरस्टैंड व्हाट आई मीन बाय सबसे ऊपर बैकेज सो बेसिकली इस यहां से जो बैकेजेस स्टार्ट हो रही हैं उनमें से जो बैकेज is going to the node which is closest to the root. How can I figure out which is the deepest package? By looking at the arrival time of the other endpoint. जिसका सबसे कम arrival time है वो जो है सबसे close होगी root के ठीक है so just by looking at arrival times of this endpoint I can figure out what the सबसे deepest package is. Now question is how am I going to build this information recursively, right? I have to find out the deepest back edge from this subtree. So I am just keeping track of the deepest back edge now. I have to find out the deepest back edge from this subtree. How will I find out the deepest back edge from this subtree? Suppose recursively I have done this information. I have figured this information. From this subtree I know the deepest back edge because after all we are doing recursively, right? When I run the DFS from here, I actually end up running DFSs from let us say these three. Yeah. So suppose I figured out the deepest back edge from this subtree. I figured out the deepest back edge from this subtree and I figured out the deepest back edge from this subtree. How can I compute the deepest back edge from this subtree? Compare all three and take the minimum, the one with the minimum arrival time, right? So this will give me an edge whose other endpoint has the smallest possible arrival time. This will give me an edge whose other endpoint has the smallest possible arrival time. This will give me an edge whose other endpoint has the smallest arrival time. Now if I take the minimum of these three, it will give me the edge which has the smallest possible arrival time which emanates from this subtree. Is this true? हाँ यहाँ से जो बैक एजेस चल रहे हैं उनको भी कंसिडर करना पड़ेगा क्योंकि यहाँ से एक बैक एज ऐसे जा रही हो सकती है तो फिर ये हो जाएगी डीपेस्ट पैकेज ठीक है तो हमें इन सब का मिनिमम लेना होगा तो अब हमारा डीएफएस प्रोसीजर क्या करेगा डीएफएस प्रोसीजर अभी तक कुछ रिटर्न नहीं करता था अब कुछ वो रिटर्न करेगा क्या रिटर्न करेगा डीएफएस प्रोसीजर उस सबट्री से जो बैकेज डीपेस्ट जा रही है तो एज रिटर्न नहीं करेगा वो एज से हमें कोई खास मतलब नहीं है वो जहां वो जिस नोड पे वो जा रही है वो एज उस नोड का अराइवल टाइम रिटर्न करेगा बस वन नंबर ठीक है okay great right so now let's write our DFS procedure right so this is our let's give it some other name to distinguish it from DFS let's call it 2EC 2H connectivity clay right so we are writing our 2H connectivity procedure once again it will take as input a particular node right when we'll okay we are going to write it as the DFS thing and I'll tell you how we have to call the DFS this 2H connectivity procedure eventually okay recall I need the arrival times of the nodes so I should maintain my arrival counter suitably right so what should I do for my arrival counter हाँ एक टाइम हमने 0 पहले सेट कर दिया और यहाँ पे क्या किया अराइवल ऑफ v equals time plus plus visited v equals 1. अब
अब एक पॉइंटर मिनिमम के लिए यहीं पे
for all w adjacent to v, same thing, for all w adjacent to v do. What should I do?
नॉट विजिटेड वाला नॉट विजिटेड में वो डीएफएस करेंगे व्हेन इट रिटर्न्स टू चेक इट.
हाँ, सो डीएफएस जो रिटर्न, अच्छा अब हमें काफ़ी सारों का मिनिमम लेना है, तो एक मिनिमम वेरिएबल रख लेते हैं. हाँ, तो डीपेस्ट बैक एज DBE एक वेरिएबल बना देते हैं. डीपेस्ट बैक एज, इसकी वैल्यू क्या रखनी चाहिए हमें? इनिशियली इसकी वैल्यू क्या रखनी चाहिए?
पेरेंट वाला है उसका जो डीपेस्ट है उससे कर लेते हैं, फिर आगे कंपेयर करते रहेंगे, जो फाइनल आएगा वो
डीपेस्ट बैक एज की इनिशियली कुछ वैल्यू रखेंगे. चलिए देखते हैं क्या रखेंगे. हाँ, arrival value of this node itself would be a natural thing to do, right? Let's set that at that. Okay, now deepest backage को हमें as I do my DFS calls, I have to kind of keep updating this variable. Yeah, so what should I do? For all w adjacent to v, do if not visited w, then what should I do? Arrival v. Then DBE equals minimum of DBE, comma DFS W. नहीं समझ में आया कुछ? हाँ? Oh sorry, 2EC. Yeah, 2EC of W. नहीं आया समझ में? ठीक है, ये हमें रिटर्न करेगा कि W से क्या आ रही है डीपेस्ट बैकेज, राइट? हमारा ये V है, ये हमने W पे कॉल किया, इट इज़ रिटर्निंग कि यहाँ से डीपेस्ट क्या आ रही है, और उसको हम इसमें हम रनिंग मिनिमम रख रहे हैं इफेक्टिवली. ठीक है, यहाँ एल्स आएगा नहीं आएगा? एल्स आएगा तो क्यों आएगा? If the node is visited, then what does that mean? What edge is it? It's a back edge. पर बैक एज का भी हमें देखना है कि वो कहाँ तक जा रही है, क्योंकि जब हमें मिनिमम लेना है तो सबका लेना है, राइट? तो हमें सबका लेना है. हाँ, ये वो वाली बैकेजेस, कुछ एजेस बैकेजेस वी से भी जा रही हैं, हमें उनको भी तो कंसिडर करना है, राइट? Right? So else what should I write down here?
If you are maintaining that DECW in some particular array, then you can write that value. Or else you'll have to write the same thing again.
We'll just write the same thing. DBE equals minimum of DEBE, comma
2ECW.
not 2EC. We are not running a arrival of W. Yeah. अब मुझे क्या करना चाहिए? ये तो हो गया, तो इससे मेरा DBE में आ गया इंफॉर्मेशन. क्या इंफॉर्मेशन आ गया DBE में? डीपेस्ट बैकेज कहां तक जा रही है. नाउ व्हाट डू आई हैव टू चेक? if DBE is less than arrival V. हाँ, क्या नहीं होगा ये? If DB is less than arrival V, then okay, then continue. then we can continue. So if db equals arrival v, then धुआं, huh? Then abort. Basically then you stop your procedure saying you found a bridge. Right? You can do whatever you want. I'll just write abort here. You should not write abort, right? You should end gracefully. But you understand what I'm saying. Basically, why have I said equal to and not greater than? Greater than or equal to? Greater होगा ही नहीं क्योंकि हमने शुरू में वैल्यू उसकी अराइवल v पे सेट कर रखी है. तो अगर वो लेस नहीं है तो इक्वल टू ही होगा क्योंकि कम ही हो रहा है db उससे. अब ये प्रोसीजर सही नहीं है. अब बताएं कौन कौन क्या क्या गलती है इसमें. He wants me to explain the else part. Why do we need the else part? You are wondering. You need the else part. Okay, great.
But why add w? What is the significance of add w to that?
What? Arrival w. Well, there is this corresponds to the else corresponds to a back edge starting from v. It is going to a node w. Yeah, w is the node which is adjacent to v. So it is going to a node w. And how am I keeping track of deepest? I am keeping track of deepest by the arrival numbers of the nodes. So that's why I am comparing it, the arrival of that node with this. ठीक है. तो इसके जो चिल्ड्रन थे उनसे कुछ कुछ आया होगा डीपेस्ट इंफॉर्मेशन और यहां से जो बैकेज आई होंगी उनका डीपेस्ट होगा. इन सब में इस समय डीपेस्ट ये वाला है. सो आई नीड दैट. And if the deepest is less than this v, then it's okay, I can continue. If it is here only, deepest is this, then this means that this edge is a bridge. अब इसमें कुछ गड़बड़े हैं. रिटर्न db चलिए बहुत अच्छा कर देते हैं. वो गड़बड़ नहीं है, that is not an error. क्या हम इस एज को कंसिडर करेंगे? हाँ करेंगे, क्यों नहीं करेंगे? वी आर लुकिंग एट ऑल द वर्टिसेस व्हिच आर एडजेसेंट टू डब्ल्यू वी, राइट. और जब हम इस एज को कंसिडर करेंगे तो वो तो हमेशा ही उससे कम होगा. हाँ? No, we cannot say anything about the arrival time of this versus the arrival time of this. I have said this before. You cannot say that this is one less than that. So basically we have to modify this so that I am not considering this edge, this tree edge. Right? So this has to be modified so that the tree edge is not considered, this parent edge is not considered. ठीक है, तो वो सोचिएगा कि कैसे कर सकते हैं ये. अब इसके बाद भी एक गलती रह जाती है, बताइए. इस प्रोसीजर को हम कैसे कॉल करेंगे? हमें किसी एक ग्राफ का 2h कनेक्टिविटी चेक करना है तो हम कोई एक रूट, कोई भी एक वर्टेक्स लेंगे, उसके ऊपर इस प्रोसीजर को कॉल कर देंगे. कोई भी किसी भी एक वर्टेक्स को लेकर उस पर आप जो है इस प्रोसीजर को रन कर दीजिए. तो बताइए कि उस वर्टेक्स के लिए डीपेस्ट क्या आएगा? डीपेस्ट बैकेज उस वर्टेक्स के लिए क्या आएगा? हाँ, उस वर्टेक्स के लिए डीपेस्ट बैकेज वही वर्टेक्स आ सकता है, उससे कम तो आ ही नहीं, उससे ज्यादा तो, उससे कम तो आ ही नहीं सकता. तो उस वर्टेक्स के लिए भी ये प्रॉब्लम हो जाएगी, ये इक्वालिटी ही आएगी. ठीक है. तो ये दो माइनर एरर्स हैं इस प्रोसीजर में अभी, विच कैन बी फिक्स्ड. राइट, केवल उस वर्टेक्स के लिए जिससे आपने स्टार्ट किया है. समझ रहे हैं मैं क्या कह रहा हूं? जिस वर्टेक्स के लिए हमने ये पूरा प्रोसीजर स्टार्ट किया है उसके लिए डीपेस्ट बैकेज. देखिए, व्हेन वी डू द डीएफएस फ्रॉम दैट वर्टेक्स वी विजिट ऑल द वर्टिसेस, all the packages, and if any coming from below cannot go to some smaller number. Clearly they are only going up to this vertex, right? because this vertex has the arrival number 0. There is no vertex with arrival number less than 0. हाँ, तो बेसिकली वो मॉडिफाई करने पड़ेंगे आपको सुटेबली. वो चीज़ एक मॉडिफाई करनी पड़ेगी यहाँ पर, और दूसरी चीज़ क्या मॉडिफाई करनी पड़ेगी कि हमें ये ट्री एज को नहीं कंसिडर करना है इसमें. Right, so there are many ways of doing it. You could perhaps have marked this edge as a tree edge, right? So you will have to think of ways of doing this. I'll leave that as an exercise. Yeah, so these are two minor things, but they are important. Your procedure would not run at all if you were to ignore them. Yeah, okay. What is the running time? कुछ नहीं किया है हमने, ठीक है. पहले भी यहाँ एक डीएफएस हो रहा था, अभी भी यहाँ एक डीएफएस हो रहा है. हम एक मिनिमम और कंप्यूटेशन कर रहे हैं, ठीक है. डीएफएस, वो डीएफएस की जगह 2EC नाम दे दिया है, उससे जो वैल्यू है उसका जो है कंपेयर करके मिनिमम रख रहे हैं. एल्स में भी एक और कंपैरिजन कर ले रहे हैं, ठीक है. बेसिकली हर एक एज के लिए कांस्टेंट टाइम और स्पेंड कर रहे हैं एक्स्ट्रा. बाकी ये इस नोड के लिए कुछ और एक और वेरिएबल्स हम अपडेट कर रहे हैं. So essentially it's the same as before. For every edge we are spending a constant amount of time, right? So the total running time is still order m. Is this clear? Right? So actually very sophisticated procedures can be built on top of DFS. Right? There are many other graph problems which can be solved in linear time. They might seem very complicated problems, but you can essentially solve them in linear time using depth first search. Right? So there is, I will mention one other problem because I have a couple of minutes. We will not of course discuss it. So the other problem is G a planar graph? Do you know what a planar graph is? You have not done a discrete maths course yet? No, you are doing it next semester, right? No, that is not sufficient, right? What is a planar graph? A planar graph is a graph which can be drawn in the plane such that its edges do not intersect. ठीक है, तो मान लीजिए मेरा ये ग्राफ था, this is a planar graph, ठीक है. आप देखिए ये एजेस मैंने ड्रॉ करी हैं, इनमें से कोई भी एज एक दूसरे के ऊपर जा रही है? नहीं. I can draw it whichever way I want, but the edges should not intersect. Now suppose this is, what is this graph? This graph is the complete graph or almost the complete graph on 5 vertices. I told you what the definition of a complete graph is, right? Complete graph or a clique. Complete, is this the complete graph? Complete graph on 5 vertices. No, why not? The edge 2, 5 is missing. 2, 5 is missing. बाकी सब edges हैं. हाँ? 1, 3 है. ये रही. 2, 5 is the edge which is missing. अब अगर मैं 2, 5 बनाना चाहूँ तो there is no way I can draw 2, 5 here without crossing. And that has nothing to do with the way I drew the initial thing. ठीक है? There is no way I can draw 2, 5. So actually this complete graph on 5 vertices is not a planar graph. ठीक है? If I were to draw it this way, it would cross with this. If I were to draw it like this, it would still cross with this edge. If I were to draw it like this, it would cross with this edge, and so on and on. So there is no way of drawing this. So, that is the question, is a given graph a planar graph? This problem can be solved using depth first search, so that you can get an algorithm which runs in linear time, order m time. So, very sophisticated algorithm, right, to check if the graph is planar or not. So, this is an example of a non-planar graph that I have shown you, right. You will learn more about this in your discrete maths course. What are non-planar graphs? What can you say about non-planar graphs? Okay. So, this is another example of depth first search, but we are not going to be taking up in this course. There is one third example which I will do in 2 minutes. So, just as I defined two edge connectivity, I can define two vertex connectivity. Just replace the edge by a vertex. A graph is two vertex connected if removing any vertex still keeps the graph connected. This corresponds to computer failures now. Instead of link failures earlier, अगर कोई कंप्यूटर जो है आपका बंद हो जाता है, ठीक है, तो अगर तब भी आपका नेटवर्क कनेक्टेड रहता है, तो then you would call it a two vertex connected. So, no matter which computer breaks down, if the network is still functioning, it is still connected, then you would call it a two vertex connected graph. Yeah. So, for instance, this would be an example of a graph. Is this two vertex connected? No. Why? Because if I remove this vertex, it becomes disconnected. When I remove a vertex, I also remove the edges incident to that vertex, clearly. It becomes disconnected. But this is a two edge connected graph. This graph is two edge connected. Yeah. So, once again the same question, given a graph, is it two vertex connected? That can be checked by depth first search in linear time again. Such a vertex is called a cut vertex, right. Bridge ka corresponding notion is cut vertex here. Okay. So, these are, so we have done in today's class, we have done one example of depth first search, which is checking if a given graph is two edge connected. There are many other applications that depth first search can be put to. I have shown you, I mentioned briefly two examples, checking if a given graph is a planar graph and checking if a given graph is two vertex connected. So, next class we are going to look at depth first search in directed graphs, right, and see how it is going to be different from undirected graphs.